Let's now take a look at resisted motion. And there's basically three different situations we could have. But remembering, resistance is always in the opposite direction to which we're moving. It resists our motion. Newton's third law. We could be moving in a horizontal line. And if that's the case, then let's say my resultant force is going to the right here. Then I know we have resistance going in the opposite direction. Therefore, the resultant force must equal negative R. We divide through by the mass, we get some sort of acceleration equation. Okay, that's the first case. Second case, we could be going up. Now, in which case, my resultant force, I would be going up. I've got the force due to gravity, mg, and I've got this resistive force as well. I would end up with minus mg minus r again. Divide through by the mass, whatever that equation turns out to be. Now, it doesn't matter that I got resistance. All these sorts of things are still the same. I mean, the greatest height is still going to happen when velocity is zero. Downwards motion. So now if we're moving down, so I'll define downwards to be the positive direction. That's where my resultant force is going. Still got that force due to gravity going down, but now resistance would be going up. And so we'd end up with something like that. The resultant force is mg minus some resistance, divide through by the mass, and there's our equation. We have this other thing called terminal velocity. So when we're going down, we have terminal velocity. That's basically when the acceleration is equal to zero, or if you like, the forces are balancing. Let's have a look at some questions. So 2020 paper, we've got a box sitting on some sort of surface here, and it's being pulled along the ground, force of 200 newtons, angle 30 degrees. And what else have they told us? We've got a resistive force of 0.3 R, and R is the normal force. So I guess that must be friction. You might recall I said that the friction is usually some multiple of the normal force. And acceleration, we're just going to make it a nice round 10 for this problem. Okay, they've given us a bit of a hint there. We're going to resolve vertically. We're going to show that R is 400. So there's our box vertically. Well, that means that force of 200 newtons I now need to resolve into horizontal and vertical forces. And if I just look at vertical, I've got 50g going down, I've got R going up, that's the one we're trying to find, but I also have 200, and it's the opposite side, so that'll be sine of 30. Now I know the resultant of all that, the vertical forces, must be zero. It's not like the box is jumping off the ground, it's just staying on the ground. So the vertical forces, or the resultant force vertically, would be zero. R plus 200 sine 30 minus the 50g, all going to add to be zero. If I make R the subject, we get our result. R is 400, which is what they wanted us to show. Now we're going to look horizontally, and they say, well, show that the net force horizontally is about 53.2 newtons. I'm going to say to the right is going to be my positive direction for this, because that's the way they're pulling, direction I'm traveling. And the horizontal component, 200 cos theta, but we also have this 0.3 R in the opposite direction. So mx double dot, resultant force, 200 cos 30 minus 0.3 R. But they've used the word net force, which is another way of saying resultant force. The result of all the forces is the net force. I don't need to know what M is for this, because it's the force they're looking for. So I'm saying that force is equal to 100 root 3 minus 120, which is about 53.2 newtons. What is the velocity of the box after the first 3 seconds? Well, I now know that mx double dot is 53.2. That therefore means that dv dt is 53.2 divided by, and now I do need to know the mass, and they told us that was 50. I don't like decimals on the top of fractions, so I've changed that to be 133 on 125. Okay, but now we can separate our variables. We know initially the velocity is 0. We want to know after when time is 3. Do some integration, and we get our result. It's 3.2 meters per second. Let's try this one. Particle, we're projecting it upwards this time. Velocity of u in a resisting medium. So, okay, there's just resistance involved. Assuming that retardation due to this resistance is equal to kv squared, just a fancy way of saying the force. Find expressions for the greatest height reached and the time taken to reach that height. Let's draw ourselves a picture. MX double dot. Remember, actual force diagrams, you don't put the resultant force on. I'm just writing it there so we know, right, that's the direction I'm taking to be positive. We have mg going down. We also have this resistive force, which they've told me is kV squared, going down. I also know that when x equals 0, the velocity is equal to u. Mx double dot, our resultant force, is minus mg minus kv squared. Divide through by the mass, I have an acceleration equation. We're trying to find expressions for the greatest height reach. So I'm going to use v to v dx, a link between displacement and velocity. Now, v to v dx makes more sense to write that all as one fraction on the other side. So minus mg minus kv squared over m. dx to v would be that. Separate out the variables. All right. X is equal to m on 2k, the integral of 2kv on mg plus kv squared. Basically, I saw it was a log situation, so I wanted to create the derivative on top. So I made that 2kv on top, which is why I then divided by 2k out the front here to balance it out. That gives me the log of mg plus kv squared. Ooh, it's a horrible answer, but there it is. It is what it is. So using our log laws, I suppose I could have left it as mg plus ku squared on mg, but I just said, well, mg on g is 1, so I've got 1 plus ku squared on mg. That's pretty much as good as I can go, unless they give me some information about what the mass is and what k happens to be and those sorts of things. So there's my greatest height. The other thing they asked me to find was the time it takes to get there. So now I'm going to go back to that acceleration equation, but this time I'll use dv to t, because that'll link velocity and time together. Again, separate the variables, but this time I've got, well, it's looking like it's going to be an inverse tan situation here. So I played around with that to make it just v squared. It makes it a little bit easier for inverse tan, but that means this mg becomes mg on k, because I pulled out the k altogether. So we end up with, well, it's the m on k out the front, but then it'll be the square root of mg on k, but 1 over that, because remember it's 1 over a, the inverse tan of, well, in this case, v over a in this case being the square root of mg on k. Substituting u, thank goodness the other number we're substituting in is 0, because that just becomes inverse tan of 0, which is 0. And we have that lovely expression for the time. The square root of m on kg, inverse tan, square root of k on mg, u. Let's do one where we're dropping. Body of mass 5 kilos, drop from height. Gravitational acceleration is g. Air resistance is proportional to speed, and they've even told us that proportion is going to be 1/8. Find velocity after time t. Let's draw ourselves up a little picture. What's happening? So I'm going to say down is my resultant force. They've told me the mass is 5, so I've said, well, okay, resultant force 5 times the acceleration. We have 5g going down, but we also have an 1/8 v in resistance going the other way. So 5 times the acceleration is 5g minus an 1/8 v. I have an acceleration equation. We want to link velocity and time. So we'll write acceleration as v to t. Write the right hand side all as one fraction to make life easier. Separate out our variables. Looks like we've got a log function on the right hand side, because we've got a constant on the top minus v on the bottom. And subbing in, eventually, we get 40 log 40g on 40g minus v. We've got to go further, because they've asked for velocity after time t. I've found something for t. I need to make v the subject of this. Okay, let's keep going. T over 40 then is the log. So exponentialize both sides. We want to make v the subject. Okay, I'm going to turn that upside down so at least v's on the top of the fraction. That means it becomes e to the negative t on 40. Multiply out by the 40g. Move the other 40g across, and we've got ourselves an expression for velocity in terms of t. It's a downward one. They sometimes like to ask about the terminal velocity. Remember, terminal velocity, well, that's when acceleration is equal to 0. That's one way I could find terminal velocity. There is another way, because what terminal velocity is, it's the limit as the time approaches infinity of velocity. So it's sometimes called the limiting velocity as well. And if we look at our velocity equation, well, as t approaches infinity, we've got that e to the negative, so that backwards exponential, that bit's going to approach 0. So I could have said it's going to be the limit as t approaches infinity of that, which is, again, 40g. There are two different ways you could find terminal velocity. Right, how far has it fallen after time t? Okay, well, now I'll go back to that velocity equation, but write it as dx dt. I want to link displacement and time together. Separate our variables, and eventually, here we go. Ooh, lovely. X equals 40 gt plus 1600 g e to the negative t on 40 minus 1600 g. Let's look at some HSC ones. What's been happening recently? So 2020 had this lovely pulley question. We've got two masses, one of 2m, one of 4m, attached by a string. And the masses are at rest, but then they're released. We have a force due to air resistance, it's kV, K is just positive. Show that dV to t ends up being this expression. Well, let's look at the two different masses. So on the left-hand side, our mass, I have 2mg going down. I also have kV. How did I know resistance was that way? Well, it makes sense. They've given us a little picture there with the V going down, so they've told us it's going down. But it kind of makes sense that the heavier one would pull the lighter one up. So we know our mass on the left is going up, and that's why resistance must be going down. But we'd also have tension in that string as well. Now, our resultant force, 2mx double dot, will be T minus 2mg minus kV. Now let's see what's happening on the right-hand side. So on the right-hand side, also a force due to gravity, 4mg, but this time resistance will be going up for this one, because that mass is moving down. So we have kV going up. It also has tension, so its resultant force, 4mx double dot, is equal to 4mg minus t minus kV. So t is that linking force. We should be able to get our expression now. So t, if I make it the subject on the left-hand side, I get 2mx double dot plus 2mg plus kV. Substituting that in over the right-hand side, now I'll make acceleration, because that's what we're trying to show, dV to t. Let's make acceleration the subject of all that, and we get our result. Well, okay, I've written mg, they wrote gm, but it is, of course, the same thing. Given that the velocity is less than gm on k, show that when t equals 3m on k log 2, the velocity of the larger mass is gm on 2k. That's what we found for acceleration. Separate out those variables. Now, left-hand side, what have we got? We've got a log function on the left-hand side, because mass is just a constant. So we'll end up with the log of mg minus kv. And on the right-hand side, we just get log 2. That's nice. The 3m on k's cancel on either side. And keep playing with it. Now, this one's okay because they told me that V is less than gm on k. Therefore, I know this mg minus kv must be a positive number, which means the whole fraction is a positive number. Therefore, mg on mg minus kv is 2. Those things must be equal, couldn't be negative 2. And we end up with V equals mg on 2k, and that's what we wanted to show. Object. This time it's got a mass of 5. It's on a slope, this one. 60 degrees to the horizontal. Acceleration due to gravity, just leaving it as g. We've got velocity of the object down the slope. Okay, so it's moving down the slope. Force due to gravity. Oh, and there's two forces. One of magnitude 2v, one of 2v squared. Both of them are up the slope. So it's got these two different resistive forces. Why they didn't just combine it into one force of 2v squared plus 2v? Who knows? This is going to be our resultant force, what we have to show. Okay, let's draw a picture. There's our block. We have gravity of 5g. We know we have this resistive force, and I have combined it into one, because you've got these two. May as well think of it as 2v plus 2v squared. I'm also going to have a normal force at right angles to the plane. It's in contact. So I know that's there too. But they've made life a little bit easy for us in that they've said, no, don't do it horizontally and vertically. Do it down the slope, which is great because then I don't need to know what the normal force is. Everything's going to be in that direction. But it does mean I'm going to have to resolve gravity now into those two forces. So gravity has become the resultant force. So it's the hypotenuse of our right angle triangle here. And then the other two sides are just in the same line as the slope. And the other one's in the same line as the normal force. Where does 60 degrees go? Playing with geometry, it would end up down there. So looking at it horizontally, then our resultant force down would be, well, gravity's going down, so that's 5g sine 60 minus the resistive force. How close are we? Very close. We just have to turn sine 60, and it is of course root 3 on 2. So we have our answer. There's one value of v, such the object will slide down the slope at a constant speed. Find the value of v given that g is 10. So it made life a little bit easier for us. Nice neat 10 rather than 9.8. Well, what do we know? If it's sliding down with a constant speed, then its acceleration must be 0, because it's not changing. Okay, well therefore, that resultant force that we just found must equal 0, because mx double dot would be 0. We just now need to find v. Oh, they told me g was 10, so that becomes 25 root 3. There's the quadratic I have to solve. Okay, we end up with a square root of a square root, but we're just bunging it into a calculator, so that's not a big deal. We can do that. Because velocity is going to be positive, it's going in the positive direction. So it couldn't have been the other case, because I would have ended up with a negative number. And that all works out to be 4.2 meters per second. Okay, so 6D, 6E will play with resisted motion.